Welcome back to another explainer. Today we're diving into this completely fascinating everyday mystery that is literally sitting right there in the palm of your hand. I mean, we use our devices nonstop, right? Texting, scrolling, searching, but how do they actually process those super basic actions? Well, today we're going to break down a core concept of computer memory, and we're using a brilliantly simple visual to do it. Let's get into the flip-flop guard, demystifying computer memory storage.
Think about this for just a second. You're texting a friend, you tap the letter A on your screen, and boom, it pops up in the message box. But how does your phone actually remember that you typed that letter, even for that tiny split second before it sends it off into the world? For a device made of just glass, metal, and tiny little circuits to actually grab onto a piece of information and hold it, that is nothing short of modern magic. We totally take this daily habit for granted, but the mechanics behind that momentary retention are absolutely mind-blowing.
Let's start with Section 1, the split-second memory.
To really wrap our heads around how this works, we're going to bypass all the complicated math and take a trip down into a microscopic, metaphorical world. I want you to imagine we're on a fantastic voyage right now. We're shrinking down, right past the glowing pixels of your glass screen, past that heavy lithium-ion battery, and deep into the intricate, bustling city of your phone's hardware. Down here, information isn't just magically floating in some cloud. It's actually physically being held and passed along by the microscopic architecture of the computer's memory.
Which brings us to Section 2, meet the flip-flop guard.
Okay, let's dive into this. In the world of digital electronics, this absolute game changer of a memory component is officially called a flip-flop. But for our journey today, I want you to picture this flip-flop not as some boring piece of silicon, but as a tiny, highly disciplined guard. This microscopic guard's entire existence, their one and only job inside your device, is to literally stand at attention and hold onto a single piece of information for you. So when you tap that letter A on your keyboard, you're essentially handing a tiny little package of data down into the machine. And it's this guard, the flip-flop, that reaches right out and catches it.
All right, moving on to Section 3, the light switch rule.
Now, if you've ever looked into computing, you've probably heard that computers basically think in ones and zeros, right? Good old binary code. And this brilliantly illustrates how we can map that somewhat intimidating math directly to a physical, super relatable action. Because to our tiny guard, a 1 simply means flicking a light switch up. A 0 means flicking that light switch down. That is literally it, on or off, up or down. But what's really fascinating here is the sheer scale of the whole thing. Because obviously, to remember an entire letter or a high-res photo or a whole operating system, well, one guard just isn't going to cut it. So I want you to paint a mental picture right now of an endless row of these tiny guards, just standing shoulder to shoulder in a massive, perfectly straight line, stretching way off into the microscopic distance. They're all standing perfectly still, hands just hovering right near their light switches, waiting for their cue. So how does the information actually travel down this line? Well, it works kind of like a perfectly choreographed wave at a huge sports stadium. The whole process happens in 3 really rhythmic steps. Step 1, a guard looks directly at the person immediately before them in line. Step 2, the guard perfectly mimics whatever that previous person is doing. And Step 3, the guard flips their own switch to match. So if the guard ahead flips their switch up, our guard flips their switch up. If it's down, they flip it down. This rapid-fire chain reaction cascading all the way down the line of guards is the absolute foundation of what computer engineers call digital logic gates. Let's really emphasize this direct rule here. Each guard can only flick a light switch up or down, a 1 or a 0, based entirely on what the guard right before them did. It is absolute strict obedience. Although, honestly, you kind of have to feel a little bad for these metaphorical guards. I mean, imagine your entire job description is just staring at the back of your coworker's head all day long, waiting to see if they move their hand so you can finally move yours. Talk about exhausting. But it's exactly this unwavering consistency that makes your phone's memory so incredibly reliable.
Let's move to Section 4, your phone's tiny army, and see how this builds.
Okay, now we need to zoom back out. We're leaving our microscopic metaphor and snapping right back to the reality of the amazing tech sitting in your pocket. Because the scale of this operation is just staggering. We are talking about millions. When you hear about gigabytes of RAM or storage in your phone, we're talking about millions and millions of these microscopic guards, these flip-flop circuits. They're constantly looking at the circuit next to them, flipping their tiny electrical switches up to a 1 or down to a 0, literally millions of times a second. They work simultaneously in absolute perfect synchronization to capture every single text message, every downloaded image, and every streaming video you interact with.
That cascading wave of ones and zeros is exactly what creates the massive, incredibly fast memory storage that powers our whole modern world.
It completely changes how you look at the device in your hand, doesn't it? The next time you rapidly type out a message to a friend, or honestly, even as you're watching this explainer right now, I want you to ask yourself, will you think of the millions of tiny guards tirelessly flipping their switches up and down, working in perfect unison just to display this final screen? It's an incredibly vast, invisible army, doing a beautifully simple task at absolute lightning speed. Well, thank you so much for joining me for this explainer. Keep wondering about the world around you, and I'll catch you in the next one.